Hi everyone, my name is Blagoj and I am part of the privacy and scaling exploration team and I work on the RLN primitive. Today I'm going to talk about RLN, high-level overview, and additionally RLN application and what we can do with it in the real world. So RLN is a zero-knowledge gadget which enables rate limiting and can be very useful for spam prevention in privacy-preserving environments. So it enables spam protection on protocol level, and it is very useful for, let's say, frequency-based spam protection and rate limiting. So it enables objective spam protection. So in use cases where we know certainly what's spam, it does not help with content-based spam protection. So how it's implemented, basically it's a multi-component gadget. It has a Zika circuit, but additionally it has like external components which are basically logics used for verification and for detecting what's spam and what's not, and some additional metadata. So it works in a few phases. The first phase is registration, the second is signaling, and the third is verification. So in order for the users to be able to send valid ZK, RLN ZK proofs and to participate in the application that uses RLN for spam protection, let's say, they need to be a part of membership Merkle tree. So RLN works on the concept of anonymity set. So a user is part of a set, but so basically they can do certain actions, but they do not reveal their identity. And also this serves as an anti-Sybil gadget, and so for example the cost of the registration can be app-specific and determined by the requirements of the application, but the goal is to have, let's say, strong anti-Sybil protection. And for example, an example for registration can be a smart contract which takes a stake, so user need to stake certain amount when their identity commitment is added into a Merkle tree, or maybe it can be a social stake, so they can use something like Interop. The goal is to basically enable some kind of hardened registration for this step. And after the users are registered, basically they can interact with the applications. And additionally, the requirement here is that with each signal, a user must generate valid ZK proof. And additionally send some metadata with the proof. So basically the message, the proof, and some other metadata such as the X and Y shares, which are necessary for verifying the proof, and also necessary to enable this spam protection mechanism. So the ZK circuit has two phases. The first one is the membership Merkle tree inclusion verification, and the second phase is construction of this linear equation where we basically encode the user secret in the first coefficient of the polynomial, and we use Shamir secret sharing scheme, for example, to be able to reconstruct the user's secret from multiple shares. So this happens, for example, if the user breaches the spam protection rules and sends more than one message per epoch. So yeah, this is how the messages look like. So the user sends a signal, and then they set a proof, an internal nullifier. I'll talk a bit about that later, and XY shares and the RLN identifier. So this is like a part of the RLN RFC, which is at this link below. And here is how we construct basically this linear equation. So the A0 is basically the identity secret, and then we construct the A1 coefficient, and additionally the internal nullifier. In this way, we have an additional parameter which is called RLN identifier, and that's used to enable, for example, cross-application protection for the user, because it might happen that a user sends proof, a valid proof for two different applications with the same epoch or external nullifier, and that way they can get slashed as well. And the third part is the verification. So this part is basically what enables the spam protection. So first, the common scheme is that the applications check for duplicates. For example, if a duplicate message is being received and basically the same external nullifier, the same internal nullifier, and the X and Y shares were seen before, then that message can be safely discarded because it's a duplicate. Then the next step is proof verification. If the proof is invalid, the message should also be discarded. But if the proof is valid and XY shares are different for the external nullifier and internal nullifier, that means that the user has breached the spam protection rules, and that we can reconstruct their secret. And basically from the user secret, their identity commitment is generated. So basically this works in a way that in the circuit we enable like this kind of secret encoding, so that later on externally we can have this kind of system that basically enables spam protection, so that, for example, if we can reconstruct the user secret, we can have, let's say, a smart contract, or maybe some kind of an external system that, if we can prove to that we can basically regenerate the user's identity commitment, we can like exclude them either from we can exclude them from the Merkle tree, either removing them from the smart contract and taking their stake, or maybe if not smart contract is used, just remove them from the Merkle tree. And so we also work on improving this gadget. So next things we plan to do is like improve the circuits, like improve the prover time, and this can be necessary for some applications which are very let's say latency sensitive. Currently, the proof generation time takes around like 1 second for Merkle tree of depth 32. And additionally, we plan to implement a generalized smart contract architecture and experiment with on-chain proof verification, and additionally expand the usage of this primitive and work on getting it more into the known. Okay, so I will talk a bit about the applications and how this gadget can be related to real-world applications. So basically, this gadget can be useful for any application that has some kind of frequency, so that the users frequently send messages to interact with, but also require some kind of privacy-preserving environment, so that the users preserve their privacy. And we've worked on a few projects and prototypes, and additionally, we've found some additional use cases which we think are quite important. So the first such project is Ethereum Consensus layer validator anonymity. So currently, validators on the Ethereum consensus layer are susceptible to metadata analysis attacks. So this means that their physical IP address can be found and they can be DDoS'd. So this means, so this is a risk certainly for, let's say, network destabilization, and can have some impact. So maybe not an impact for the large, let's say, staking providers where they manage like advanced networking setups, but maybe for small validators, this can be problematic and maybe can lead to centralization in the future. So how we think about solving this issue is enabling a private network so that the validators can obfuscate themselves. So the original, let's say, consensus there, a message sender, for example, the validators have multiple, can have multiple roles, for example, block proposer, a tester. They can also do aggregation, attestation aggregations, and that kind of stuff. So the goal is to obfuscate the validator, and how we plan to solve this is by introducing a private network where only the validators can register and can send messages to this private network. We plan to use the Dandelion method for this. And the problem in this network is that it's not spam resistant, so we can enable, let's say, spam resistance by enabling RLN. So it can also serve as an, let's say, a way for registration of the validators, and then we can detect spam here. And also additionally, if we detect spam on this network or at this part of the network, this might translate to, let's say, have some useful properties later on to the network, and maybe some kind of optimizations to the consensus layer itself can be made. An additional use case is like peer-to-peer protocols in general. So Oscar gave a presentation on Waku yesterday, and there they have a, let's say, privacy-preserving peer-to-peer protocol where they want to replace the gossip sub extended validators and peer scoring rules with RLN as a, let's say, as a stronger mechanism for preventing spam and having some kind of more global and stronger spam prevention. Additionally, this can be useful for instant messaging application. So for example, we can also enable, let's say, application level spam protection if we have, let's say, a messaging application which requires user anonymity. There all the users are anonymous, and we can basically we cannot figure out like who should we let's say remove. Or additionally, if we have identifiers, so for example, as the status application, status IAM, this can also be helpful, because like there we have very let's say weak anti-Sybil measures. So the application is constantly spammed. For example, here are some like examples from the status application. But additionally, we've worked on a project called Zika Chat, which is basically anonymous chat applications, and we have several use cases there. For example, private and public rooms, and we use Interapp for registration. So let's say currently, an example use case is let's say a group of, let's say, people that have a Twitter account with 5K followers can register, and then they can chat into this application in anonymous way, and we might extend this to other groups and use cases. Another interesting use case is a CAPTCHA replacement. So CAPTCHAs are a huge burden, UX burden, both for the users and businesses, and a lot of time is spent on solving this. But CAPTCHAs exist because they prevent basically bots for using content. So basically, they help distinguishing humans from bots. But we can solve this by using ZK proof instead of CAPTCHA, basically, and this can be a good can have a better UX because the users themselves do not need to do anything. A ZK proof can just be generated by their browser, and this can be achieved with RLN because the latencies are not so big for this use case. And an additional use case is API request rate limiting in general. So basically, services that work on an API API key request basis. So, for example, if you need to be authorized to access their services, you're given an API key. But in certain scenarios, let's say RLN can enable a good spam protection and overuse of these services. So, for example, if we take, let's say, Fura, they have a free package where you have, let's say, 100K requests per day, but you can generate multiple such keys and you can rotate them and abuse their services, for example. But if you have, let's say, a stronger Sybil measurements and anti-Sybil measurements and have a stronger spam protection, you can prevent this. And yeah, so that's it. But additionally, there's some certain other use cases that we've used. So, for example, key exchange bundles, RLN can be useful for that kind of use cases. And additionally, maybe mempool spam prevention for certain, let's say, protocols. And I believe there are other use cases that can be solved by RLN. So yeah, I've put some resources here that you can check. Yeah, so that's it.